So we've learned about low-pass filters in the previous video. Let's talk about some other kinds of filters. So our low-pass filter, remember, looked like this, where this is in, this is out, and our gain equation came because we were measuring the voltage across this capacitor, and that gave us ZC in the numerator of our fraction, right? ZC over Z total. Instead, if we switch these components, so we have a circuit that looks like this, so capacitor and then a resistor to ground, and this is our output, our fraction changes. Instead, we have R over Z total. So the Z total looks the same. That's still the square root of R squared plus 1 over omega C squared. But we have this thing in the numerator that's not changing with different frequency. So it turns out if we do the math for this, we can figure this out without too much trouble. So Z total here is the impedance of the capacitor plus the impedance of the resistor. So at low frequencies, the impedance of the capacitor is very high, so Z total is very large. At high frequencies, the impedance of the capacitor, 1 over omega C, is very low, and so Z total is approximately equal to R, so we get R over R. So this does the opposite of a low-pass filter. This is a high-pass filter. It allows high frequencies to pass through it and blocks low frequencies from reaching the output. What else to say about that? We can. I'm not going to write down the equation. If we want to, we could plug in R and Z and get an expression for the gain, but we're not going to worry about it. We're just going to look at this graph, which looks basically exactly. This is gain and this is frequency, and this looks exactly like a flipped version of the low-pass filter. It's really low gain up to some point when the gain goes up to 1, and the 3 dB point is still when this is, 1 over root 2, a factor of 1 over root 2 smaller than the maximum. So this is a high-pass filter. And we'll talk about applications of low-pass and high-pass filters in a little bit. But right now, I want you to fully appreciate the abilities of remote learning and recorded lectures, because what we're going to do is I'm going to apply high-pass and low-pass filters to my voice on the video when I'm doing this. So, okay. This is what my voice sounds like passing through a low-pass filter. This is what my voice sounds like passing through a low-pass filter. This is what my voice sounds like passing through a high-pass filter. This is what my voice sounds like passing through a high-pass filter. Okay, so this doesn't really tell you about the application in electronics or audio engineering, but at least it maybe gives you a sense of what one might be able to do with such a filter. Okay. So let's look at two more filters, two more important kinds of filters. The first is they're both gonna involve inductors and capacitors. Okay, so again, without actually analyzing this or writing down the equations, we can kind of guess at what's going on in here, right? So we're measuring across this output, and that means in the numerator of our voltage divider equation, we just have an R. In the denominator of this equation, we have the total impedance, that is R plus the impedance of the inductor plus the impedance of the capacitor. And these are complex numbers. So we know that at a certain frequency, these two exactly cancel out, right? At the resonant frequency, these two exactly cancel out. So at some special frequency, F naught, our gain is just R over R, which equals 1. If we are above or below that frequency, one of these is going to be bigger than the other, and if we are far enough away from that resonant frequency, one of these is going to be much larger than the other, and much larger than R. So the result of that is that as we move away from this resonant frequency, our gain goes from 1 down to 0 in either direction. So, well, I guess we can write down the full equation because it's not that bad. So if I plug in for things here and I take the magnitudes, we get R over the square root of R squared plus omega L minus 1 over omega C squared. And you can derive this for yourself, but this is what the response of this filter looks like. This is the gain of the filter. Okay, so at very high frequencies, ZL is really big and the gain goes to 0. If omega is really small, then ZC is really big and the gain goes to 0, right? Because ZC is in the denominator too. So if omega is just right or really close to this resonant frequency omega naught, then V out is approximately equal to V in. So our gain graph looks kind of like this. So there is a range of frequencies, and we've already talked about what this range is, right? This is the bandwidth. There's a range of frequencies within the bandwidth of this resonant frequency that is allowed to pass through the filter, and everything else out here, above or below this, is blocked by the filter. So this is called a band pass filter. Also, they call them pass band filters. I don't know. So this is a band pass filter because it allows this band of frequencies to pass through it and everything else gets blocked. And we know enough about characterizing this circuit from previous videos that we can calculate what the bandwidth is and what the resonant frequency is, and we could calculate, the quality factor Q and stuff like that. All right, band pass filter. The last kind of filter, similar to the band pass, is the band. Oh, I shouldn't give it away. And there are different ways to draw these filters, but we'll draw them the way they're in my notes. So we have our resistor up here, and we have our inductor and capacitor connected to ground. So here, at the resonant frequency, the impedance of these two is going to cancel out, and that's what's in the numerator of our voltage divider equation, right? So right at the resonant frequency, the numerator is 0, Z total is at least R, and so 0 over R is going to give us a gain of 0. Omega naught or F naught. I'm not being very consistent, but hopefully you understand that it's just a difference of a factor of 2 pi, and we could always figure out one if we know the other. So if we move further away from the resonant frequency, then these two aren't the same anymore. One of them is bigger than the other, and we start to get a signal. And if we're really far away, well then ZL or ZC is much, much bigger than this resistance if we get sufficiently far away. And so our gain, is some big number over that big number plus the tiny resistance, which is still the big number. So we get a ratio of 1. So the gain equals 1, far from F naught above or below. So our gain plot for this looks like this. We have a gain of 1 at most frequencies, but within the bandwidth of this resonant frequency, these frequencies are stopped by the filter. So this is called a band stop filter. And for some applications, if this is super narrow, this is called a notch filter also. That's a really common expression, a notch filter. All right, so these are our 4 different kinds of filters. And in the next video, we're going to talk just a tiny bit about applications and some other things we can do with filters. All right, I got this video all edited and ready to post online, and then I felt bad that I didn't include my voice with a bandpass and notch filter. So let's do the same thing just for fun. This is my voice through a bandpass filter. This is my voice through a band stop or notch filter. This is my voice through a band stop or notch filter.